There were a lot of questions in class on application exercise 2.5, allocating cleanup efforts. And this is an application of that second marginal principle from the textbook. And basically that principle states when we're looking for the cost-effective solution, that is, given some cleanup target, what's the lowest cost method of attaining that, that the low-cost cleanup method will feature equalized marginal costs across all firms cleaning up, all methods being applied to clean up, however you want to put it. That equimarginal principle would states definitively that if we're minimizing costs, that our marginal costs across all possible ways of doing it are equal. And the logic, remember from a few class periods ago, is that if that weren't the case, there would be a way to reduce cleanup in the high marginal cost area, increase cleanup in a low marginal cost area, and get the same amount of cleanup for less cost. So let's get into the nitty-gritty of this problem. So we currently we're emitting 6,800 tons of sulfur dioxide. We want to clean up half. And we have three possible methods of cleaning it up, and we have three marginal costs. And notice that the key feature here, that each marginal cost increases with the amount of that method we use. So method 1 has marginal costs that increase more slowly than the marginal cost of methods 2 or 3, but all three methods feature rising marginal costs. And that's critical to understanding this problem. So let's dive in. When you're struggling with a problem, one of the first things you do is just write everything you know down. And we know that cleanup target is 3,400 tons of smog. So I know, oops, I'm in a pointer instead of a writer. We know that Q1 plus Q2 plus Q3, the total cleanup is going to have to measure to 3,400 tons, half of 6,800. All right, so we know that. And then what else do we know? Well, this is where we apply that equimarginal principle. We know that MC1 is equal to MC2 at the optimum. And we also know that MC1 is equal to MC3. MC2 and MC3 are also equal to each other, but we don't really need to write that down because it's not going to factor into how I'm going to solve it. So from this MC1 equals MC2, I know that MC1 is 0.01 times Q1, and I know that's going to equal 0.02 times Q2 by the equimarginal principle. And I just want to solve everything into a form that I can substitute into this equation, all in terms of one of the variables. David did it by Q2, which is perfectly fine. I'm going to do it for Q1. You could do it for Q3, whatever. But anyway, notice that I divide through by 0.02. And what do I get? These cancel, and I'm left with Q2 is equal to 0.01 over 0.02. 0.01 over 0.02, but that's just 1 over 2, otherwise known as half, which is 0.5 times Q1. So that's going to be helpful. I'm going to put a square around it just so I can come back to it easily. Then finally, by that same logic, not quite finally, but second to last step, we know that 0.01 Q1 is also equal to 0.05 times Q3. All right, so I can divide both sides by 0.05. This is talking and thinking again. 0.05. So these babies cancel. So I'm left with Q3 is equal to 0.01 over 0.05, but that's just 1/5 otherwise known as 0.2, 20%. So here we have Q3 is equal to 0.2 Q1. Like I say, David did it in terms of Q2, and that was perfectly fine, and he got the right answer. But Q1 is maybe a little bit easier. I don't know. It's 6 of one, half a dozen of the other. All right, so now I can, in this first equation, I've got an expression for Q2 in terms of Q1. I've got an expression for Q3 in terms of Q1. I can substitute both of these, into this first equation, and then I've got one equation in terms of Q1 and one unknown that I can solve for a unique value of Q1, and then I know that Q2 is going to be half of whatever I get for Q1, and Q3 is going to be equal to 20%, 1/5 of whatever I get for Q1. So we're almost there. So Q1 plus Q2, but Q2 is also equal to 0.5 Q1. And Q3 up in this equation, but Q3 is also equal to 0.2 Q1. All that's equal to 3,400. And that's also, if I add those up, this is 1 times Q1 plus 0.5 times Q1 plus 0.2. That all together is 1.7 times Q1. That's equal to 3,400. Divide both sides by 1.7. These cancel out. Q1 is equal to 2,000. That means, remember, Q2 is just half of that. Half of 2,000 is 1,000. And Q3 was 0.2 times 2,000. That's otherwise known as 400. And then that's my answer. So again, we take a problem that looked really hard at the beginning, but once you write down everything you know and apply that equimarginal principle critically, it turns into a fairly straightforward problem.